that y'all want to go over from homework or anything?
Not really. I understood everything we were talking about yesterday.
Awesome. That's great.
Yeah.
So that means that we gonna understand everything today because we just built it.
Hopefully.
Yeah.
You know how things get twisted up, but I know that I can ask questions, even if it's a
Mhm.
dumb question.
Nah, no, no such thing. No such thing.
Exactly. I think I feel more comfortable when I have you like explain it again in a different way.
I got you. No worries. No worries. So we're gonna start off with standard units. Oh, I clicked on the wrong
What
thing.
chapter is this?
Oh, we still in seven.
Okay. Yeah, because yesterday you said it was chapter something else.
Yeah, because we jumped back to algebra for a sec, and then we brought it forward. Yeah. But what we were talking about yesterday is relevant to like today's conversation and going forward.
Okay.
Yeah. So let me just get this up.
I don't think nobody's aware of class right now.
I mean, I sent it out, but it's all right if they're not. I mean, the jollof rice thing probably still going on, so I'm
Oh,
not even mad at that. If they eating, I'm happy.
Grace, I cannot.
Uh,
Yeah.
all right, so we talking about standard units and areas under the standard normal distribution. So let's talk about z-scores and raw scores. All right. So normal distribution varies from one another in two ways. The mean, mu, may be located anywhere on the x-axis, and the bell shape may be more or less spread according to the size of the standard deviation. The differences among the normal distributions cause difficulties when we try to compute the area under the curve in a specified interval of x values, and hence the probability that a measurement will fall into that interval. So it would be a futile task to try to set up a table of areas under the normal curve for each different mu or sigma combination. We need a way to standardize the distribution so that we could use one table of areas for all normal distributions. So we achieve this standardization by considering how many standard deviations a measurement lies from one mean. In this way, we can compare a value in one normal distribution with a value in another. So different normal distributions. The next situation shows how this is done. All right. So this gonna be good. 1 sec. Okay.
So we gotta do a table again.
No, no, we're gonna be using a table. So we're gonna jump back to the formula sheet. We're gonna have a little formula sheet lesson as well.
Oh, with the standard deviation and the mean of the.
Right. Or with the normal distribution.
Okay.
Yeah, you gonna see. You're gonna see. We're gonna get into it. Just check something out real quick. All right. So here we go. Boom. So suppose Tina and Jack, right, are in two different sections of the same course. Each section is quite large, and the scores on the midterm exams of each section follow a normal distribution. In Tina's section, the average mean was 64, right? So that means that on average, if you take up everybody and you add them, all their scores together and divide by how many people took it, they got a 64. And her score was a 74. In Jack's section, the mean was 72 and his score was 82. Now, both Tina and Jack were pleased that their scores were each 10 points above the average of each respective section. Yay, they smarter than their classmates. However, The fact that each was 10 points above the average does not really tell us how each did with respect to the other students in the section, right? So in this next figure, right, we're going to see a normal distribution of the grades for each section, right? So Tina's 74 was higher than most of the other scores in her section, while Jack's 82 is only an upper middle score in his section. So Tina's score is far better with respect to her class than Jack's score. So let's take a look at the picture and we can see that. All right, I'm gonna bring that up right now. 1 second. Okay, that's good.
Professor, I see that in the formula sheet it says Z and stuff like that. You're gonna teach us about
Perfect.
that, right?
Yep, that's what we're getting into.
Okay.
But we kind of building up to it though a little bit.
Okay.
Yeah. So here goes the figure that we were talking about before, right? So let's make some observations, right? So this is Jack's class and this is Tina's class, right? Now, you see how Jack's class is more spread out,
Mm-hmm.
right? So yeah, he did do better than majority of the students in the class, but you see his better is not that much better. You know, it's still in the overall like middle portion of this graph, you know? Like it's still in like this middle portion of the graph. Whereas Tina did exceptionally well. Because you see majority of her class is like right here. And she done jumped outside of that, you know? So her standard deviation is smaller than Jack's standard deviation, right? Like there's sections standard deviation, I mean to say.
I understand.
All right.
So it doesn't matter like how it doesn't matter how it looks. It just matters where in that graph they are in, right? Because if Jack was a little bit more towards the end, he would have
Then
been
he'd be
king,
like in
right?
Tina's conversation, you know?
But he's not. He's a little bit
Right.
where Tina's class is.
Right.
Got it.
Mhm. Yeah. I mean, this is also like when you hear them tell you stories about, oh, like these people took the SATs or they took the NCLEX or something like that, and they made like a mean and a standard deviation score. That's for that particular year, you know, and then wherever you fell, you know how good or bad you did,
hmm
right? So they don't make a mean and a standard deviation score for every test ever taken. They do it for like the year that it was administered, right? And then it's you versus everybody else in the country kind of situation.
Oh, wow. Okay.
Mhm. Yeah. So the preceding situations demonstrates that it is not sufficient to know the difference between a measurement X value and the mean of a distribution. We need also to consider the spread of the curve or the standard deviation. So, what we really want to know is the number of standard deviations between a measurement and the mean. The distance takes both the mu, the population mean, and sigma, the population standard deviation, into account. Right? So we can use a simple formula to compute the number z of standard deviations between a measurement x and the mean mu of a normal distribution with a standard deviation sigma. So real quick, z, right? Z is the number of standard deviations a number is from the mean, right? It's how many standard deviations a number is from the mean. right?
Wait, Z is how many standard deviations,
Right? A number is from the mean.
a number is from
Mhm.
the mean.
Now, we kind of encountered this earlier in our conversations. I think not yesterday, Tuesday or something. When we had that question and I was telling you guys like, "Oh, like I'm not sure how to get it without using a trick and all of that," right? So this is the trick that I was using to get the answer overall, right? Um I with the empirical rule, right? I know definitely that Z is one or two or three, right? Like period. That's it. I know Z is that whole number. But what happens if Z is like 2.18 or like 1.92? You know? I'm just making up off the top of my head, but like if Z is some funny number that's not a definite one, two, or three, how do I get that area under the curve? This is how. This is the trick that I was using to do it. You know?
Mm.
Yeah. All right.
So what you really want to know is the number of standard deviations between a measurement
Hmm.
and mean.
Yep. So let's look at this. The number of standard deviations between the measurement and the mean is equal to the difference between the measurement and the mean divided by the standard deviation. All right. So the number of standard deviations between the measurement and the mean, right? Which we said was what letter again?
Z.
Z is equal to the difference between the measurement and the mean. So the
O
measurement and
U
the mean divided by the standard
O.
deviation.
I'll be forgetting their name. I'm sorry.
What?
U and O.
Oh, this is mu.
Yeah,
So
mu.
it's spelled like this, mu, right? And then this one is sigma, sigma. Yeah. They're Greek, actually, Greek letters. Yeah.
X minus mu.
A matter of fact, though, right? Like I think that's the next food off that we have. We need one of those. We need a Greek food off. That's what we need, man.
I never had Greek food.
Yo, it's amazing.
Really? What is it
Yeah.
like?
So you ever hear people talk about like Mediterranean diet, Mediterranean food? Like that's the Greek
I've
food.
never had Mediterranean food either.
Yeah, it's really fresh, really good. Like it's
Well, I would like that.
think fruits, vegetables, and meat, you know.
Wow, I need to do that.
But what's interesting is that their style of seasoning is different from ours.
What
You know,
is it?
like they use other seasonings that we wouldn't think to use and put things where we wouldn't think to put them. So it's like a new experience.
I would like to try that.
Yeah,
I don't care about nothing. I just don't eat seafood.
yeah. I know my handwriting not so pretty, so that's what I was trying to say.
Oh, it look good, Professor.
It looks good. Oh, I appreciate you.
No, I'm talking about naturally. I talk about the food.
Oh yeah, 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 yeah. Yeah. We need one of those at school, like a Greek cook-off. That'd
They
be
should
real
have
nice.
different. They should have a buffet up in school.
Yo, that would be the truth right there.
Hi,
A really nice buffet.
Professor.
Hey, how you
Hello.
doing?
Yes, I would like to say that like I'm in motion and the fact that you posted up that we're gonna be on Zoom at 1 o'clock, honestly, is
I
pretty
apologize
inconsiderate.
for that. I
Like,
really
so now I'm gonna
apologize.
end up missing this class because I have to log out this computer and move my car.
It's all right. I'm recording it. I got you. No worries. I got
So
you.
I don't want to be marked absent.
No, no, no. I
And
got
I'd
you. You're good. You're
appreciate it
good.
if
You're
it'll
good.
be at least 2 hours in advance because I
I
work on
know.
Rikers Island
I
and
know.
I
I
can't have
know.
my computer and stuff. So when I get these messages, it's like,
I got you. I got you.
so I don't mean to come through here a little frustrated, but yeah, I kind of am frustrated.
I got you. I got you. I got you. No worries.
But thank you, and I guess I'll see you next class.
All right. No worries. No worries. All right. Let's see. All right. So we got the z value or the z-score. So also known as a standard score, gives the number of standard deviations between the original measurement x and the mean mu of the x distribution. So this is the formula right here. All right. What I was trying to write earlier.
Right. We did it. Oh.
Yeah.
So when do we use this formula? When you want to what?
So I have a like an X distribution, right? In this case, right, we were talking about Jack and I forgot what the girl's name, Tina's sections were, right? So think of Jack's section as like a X distribution and Tina's section as another X distribution, two different X distributions. And I want to compare them, like right now, visually speaking, we could look at the graph and tell like, all right, Tina did better than Jack. But it'd be a lot easier if we had like a number to say like, all right, Tina's
So we
number is
gotta,
higher than Jack's.
so I'm looking at so it says in Tina's mean, it was 64. So you will have to X minus 64, right?
Mm-hmm. The
Over,
only the only issue is that in that picture we weren't given a standard deviation, but that's okay.
right.
It's just the picture for now. But in the future though, our questions we're gonna be given a standard deviation.
Okay, you're gonna show us today, right?
Yeah, yeah,
Okay.
yeah. All right, so the mean is a special value of a distribution. So let's see what happens when x is equal to the mean mu to a z value. So we have the formula z is equal to x minus mu over sigma, which will be equal to mu minus mu over sigma, which is just zero. So the mean of the original distribution is always zero in standard units. This makes sense because the mean is zero standard deviations from itself, right? An x value in the original distribution that is above the mean mu has a corresponding z value that is positive. So again, this makes sense because a measurement above the mean would be a positive number of standard deviations from the mean. Likewise, an x value below the mean has a negative z value, right? Because it's a negative distance away from the mean, right?
So what it's basically saying is that formula is always zero.
If the mean is if the x is equal to the mean, yes.
If the
Mhm.
hold on, if the x is equal to the mean,
Yeah.
then
I just want to put this all in like a nice little table so y'all can see. Make it a little bit more presentable.
so if the x equals, can you give us an example of that?
I got you. We coming up to one. We coming up to one. I
At the original
just
distribution
want to make it look a little nice, you know? One second.
in standard units.
So table 7.1. So X values and corresponding Z values, right? So if the X value in the original distribution is equal to the mean mu, the corresponding Z value is going to be equal to 0, right? If
Oh,
the X value is bigger or greater than the mean, then the Z value is going to be bigger than 0. It's going to be positive, right? If the X value is less than the mean or smaller than the mean, then the Z value is going to be smaller than 0, right? Or negative. Make sense?
hold on.
All
Uh,
right.
I'm gonna write this down so I
All
can
right, no
understand.
problem. Take your time. Take your time.
So X equals U. It can be equal, greater, or less. And C is always gonna be greater. I mean, it's gonna always be 0.
So before we jump into an example, and it's a good one right here. It ain't jollof rice, but it's a good example,
I'm about to eat dinner early. I'm hungry.
right?
Oh, I'm interested to see how this plays out. X equals
Let's
me.
just talk about what the standard score tells us. All right. So a standard score or Z-score of a measurement tells us the number of standard deviations the measurement is from the mean. A standard score close to 0 tells us the measurement is near the mean of the distribution. A positive standard score tells us the measurement is above the mean. A negative standard score tells us the measurement is below the mean, right? That's going to kind of matter to us in a little bit because our table is actually split just like that, right? We have a positive z-score table and we have a negative z-score table. So this kind of knowledge is going to help us in the future.
So a standard score of or Z,
Hmm.
a standard score closer to 0 tells us the measurement is near the mean. So
Right.
close to 0 equals near the mean.
Hmm.
Near mean. And then a positive standard score tells us is above the mean.
Hmm.
And the mean is the U and X axis, right?
Right.
Mu and X axis. So a positive, positive and negative, it's under, above and below. Is below mean. The negative is the below, right?
Hmm. It's our example that we're going to get into. But yeah, negative is below, positive is above.
Okay.
So good to go.
This is for the standard score only, right?
Right.
I'm gonna put them.
So let's look at this example. All right. So a pizza parlor franchise specifies that the average mean amount of cheese on a large pizza should be about 8 ounces and with the standard deviation of 0.5 ounce, right? An inspector picks out a large pizza at random in one of the pizza parlors and finds that it was made with 6.9 ounces of cheese, right? So assume that the amount of cheese on the pizza follows a normal distribution. If the amount of cheese is below the mean by more than three standard deviations, the parlor will be in danger of losing its franchise. Ah, so how many standard deviations from the mean is 6.9, right? And then is the pizza parlor in danger of losing its franchise? All right. Yo, this example right here kind of hits home for me. Y'all ever ordered Domino's pizza? Anybody?
Mhm.
Yo, I swear to you, like if you order a cheese pizza from Domino's and you order a regular pizza pie, right? I mean, excuse me, another pizza that has like toppings on it, pepperoni, whatever, right? Yo, the cheese pizza always weighs more than the one that has toppings.
You are too much.
Yo, I'm telling you that like they be getting us for our dollar.
I'm so weak.
Yeah. Man, next time I feel like asking them like, yo, listen, put the toppings on the side. I'm gonna put them on when I get the pizza, and then that's it. They don't need to be baked together or nothing.
I'm weak. Imagine.
Right? Because I notice like when I go to my local pizzeria, I they always take a slice that's already made, right? And then they put in whatever toppings I want and they bake it. And like when I get that slice of pizza, that slice of pizza is heavy, compared to a regular slice. Like that's the way it's supposed to be,
Right.
you know? But all right, let's calculate this real
That
quick,
whole
right?
pizza.
So let me just get my highlighter. Hold on one second. Okay. All right, just give me a second. We just loading up here a little bit. All right, let me try it again.
So we gotta use that formula you gave us, right? The standard
Mm-hmm.
score formula.
Yes. I
Okay.
just want to
We'll put Z
just want to highlight what we have real quick.
is
So our average mean,
is
8
8 ounces.
ounces, standard deviation of 0.5 ounces, right?
Mhm.
And we have 6.9 ounces, right, of cheese, right? Now, we want to know how many standard deviations from the mean is 6.9. Let's get to that formula. So the formula is Z is equal to, let's get these out the way. They're annoying. X minus mu over sigma. So what's my X? My X is going to be
8 ounces.
not 8 ounces.
Wait, I'm so sorry. That's the U.
Right. This my mean. This my standard deviation.
Okay, let me
And
see.
that's my X. I should
So
have put those in a different color. Well, it's
mean,
okay.
standard deviation. Oh, and X.
Mm-hmm.
Okay, so it's gonna be Z equals
Mm-hmm.
0.9
Good.
minus 8
Good.
for 0.5.
Perfect. And then type it in the calculator, and that's it.
Yeah, let me get my calculator.
I'm gonna do it real quick on my end. So I got what 6.9 minus 8
It's negative point
by 0.5. What you got?
negative 1.1. Why it came out negative?
I got negative 2.20.
No, I got negative 1.1.
Or maybe you did the top.
Oh, I didn't. Yeah, I just did the top. Sorry.
Got you. And then divide by 0.5. Yeah.
Hang on. Divided by 0. I got the same.
Awesome, right? So now what is this number telling us? The number is telling us that the this pizza that somebody randomly took out has 6.9 ounces of cheese on it, right? So 6.9 is negative 2.2 or negative 2.20, excuse me, standard deviations from the mean, right? But you see, they have to be more than three standard deviations to be in danger of losing their franchise. So they're good, right? They're good.
So they had to be negative 2.20 from losing their partner.
They have to be negative three or better. Well, actually more than negative three standard deviations to be in danger.
I'm confused.
So if that number that we got for Z, if that number was let's say negative 3.01, right? The parlor would be in trouble and they could lose their what you call it, their franchise, right? But because it's only negative 2.2, they're okay.
Mm.
Hmm.
Okay.
Hmm. I
So
mean,
if it
don't
was
get
a
me wrong,
if it was positive, it's a problem.
no, if it was positive, they're good.
Okay.
Yeah, yeah, they're good if it was positive. I mean, as a customer, I want that joint to be positive. Like I feel like they jipping me when it's less than the mean.
Mm-hmm.
Yeah. So the amount of cheese on a selected pizza is only 2.20 standard deviations below the mean. So the fact that Z is negative indicates that the amount of cheese is 2.20, excuse me, standard deviations below the mean. So the parlor will not lose the franchise based on the sample, right? But for me, they definitely lost my business because that's not what I want. I like my cheese, yo.
Right? It makes the pizza. I like the sauce too.
Me too. Yeah. I mean, yo, keep it 100 with you. Cheese is probably the only reason why I won't go vegan.
Where the taste good.
Mhm.
We got cheese, mac and cheese, lasagna,
Exactly.
everything good.
Exactly. I need my cheese. I mean, I'd be so bad. I will dead like take a pack of cheese and just go slice by slice.
Mm-hmm.
Yeah. I think earlier this week I had some Havarti cheese. I don't know if y'all ever tried that. It's a good cheese.
No,
Yeah.
party.
I be kind of fancy with my cheeses.
I see.
Yeah. All right, so we have seen how to convert from X measurements to standard Z units. We can easily reverse the process to find the original raw score X if we know the mean and the standard deviation of the original X distribution. Simply solve the Z score formula for X. So, given an X distribution with mean mu and standard deviation sigma, the raw score X corresponds to a Z score is X is equal to Z times sigma plus mu. All right. Now, to be honest with you, remember when we were doing literal equations?
Yeah.
When we were doing literal equations, all of this is on your formula sheet. But
Yeah.
what I don't like about the formula sheet is that the formula sheet really just reprinted the same formula, right? So say I have this literal equation right here and I just want to solve for x, right? It's the same thing, right? What am I going to do? I'm going to multiply by sigma, right? Because I want to get x by itself. What you do to one side, you got to do to the other. So now I got z sigma is equal to x minus mu, then I'm just gonna add mu over here. I do to one side, I gotta do to the other. So now what do I got? I got x is equal to z sigma plus mu.
Professor,
Right?
you told me off.
Same thing. All right. Well, what I'm trying to say, they give you this formula that they call raw score, but it's the same z formula, right? They
At
all you
this
did was solve
score,
for x, you know. So y'all have enough math to recognize that. So I just wanted to point that out. That's all.
so the raw score is the same thing as the standard score.
Yeah. Same formula, just manipulated. That's all. That's all that is.
That's crazy.
Yeah.
Like that. So why put it there?
Um, you know why I think it's there? You know the people that's taking like Math 23, like not y'all. I mean like the people that's like in just 23, not 23.5, they wouldn't know the difference. But y'all know the difference because y'all smarter, you know? That's what that is.
Mm-mm.
I don't know why that just happened. Okay, here we go. All right. Let's do some examples real quick, all right? So Rod figures that it takes an average mean of 17 minutes with a standard deviation of 3 minutes to drive from home, park the car, and walk to an early morning class. So one day it took Rod 21 minutes to get to class. How many standard deviations from the average is that? Right? And is the z value positive or negative and explain, right? So let's look at it. So the number of standard deviations from the mean is given by the formula z is equal to x minus mu over sigma. It took him 21 minutes one day to do it. On average is 17 divided by 3, which is standard deviation. That came out to be 1.33. So the z value is positive, right? So we should expect a positive z value since 21 minutes is more than the mean of 17. Make sense?
Yeah, it's basically what you showed us, right? Just
Mm-hmm.
one way or the other.
Mm-hmm.
But why does it give you two different answers then?
What do you mean? What's the second answer?
That is the same thing, but this one gives you 9.5 and this one gives
Oh,
you
so we didn't get to that second part yet. So now this is the second formula, right? So a little bit different, right? Say we had a z value, right? So what um what commuting time corresponds to a standard score of z is equal to negative 2.5? So now I'm giving you the number of standard deviations. I'm giving you negative 2.5. But I want you to tell me negative 2.5 is about how many minutes, right? Like so you kind of switching it up a little bit, right?
Mm.
And then it says interpretation, could Rod count on making it to class in this amount of time or less? So now we're using the raw score formula. So x is equal to z sigma plus mu. Just plug it in. Z is negative 2.5. You already knew the standard deviation was 3, mu 17. Little math, boom, boom, boom. We get 9.5 minutes, right? So no, the commute times at or less than 2.5 standard deviations below the mean are rare, right? So we know, remember from the empirical rule, right? If we go 3 standard deviations out, like that's almost the whole deviation, right? Remember that 3 standard deviation was like 99.7% of the data. So negative 2.5, it's not 99% of the data, but it's kind of close to it, you know? So this would be rare that this could occur, that this could happen. That's what this is trying to say. Yeah.
Mm.
Questions on this?
Sorry, I'm trying to read this. and understand it a little bit more.
Got you.
So it took him 21 minutes to get to class, right?
Mm-hmm.
It's the mean is 17 minutes on average.
Mm-hmm.
So you gotta not okay, so on average. And then the three, it takes him to drive home. So basically he's just 1 minute and 33 seconds difference.
Mm-hmm.
Okay, and
Well,
then
not 1 minute and 33 seconds. 1.33 is the number of standard deviations it took him from the mean, you know?
so how would you translate that? Standard deviation would equal to what here?
It's three, right? So how many 3 minutes from 17 minutes did it take him to get to class that one day when it took him 21?
So 1.33,
Right.
but you wouldn't call that minutes, right?
That's not minutes, no. Yeah,
That's that.
Z has no unit really. It's just the number, it's a count. It's how many standard deviations something is from the mean. That's all it is. Yeah.
Mm. And then the second one, what commuting time corresponds
Mhm.
to the standard score of Z equals negative 2.5 interpretation. So this, so what does that mean? What commuting time corresponds to a standard score of Z equals negative 2.5?
So that's the reverse, right? So I'm giving you a Z score, right? Which again, it has no unit, like we know that it's a measurement of how far the
So
person,
now,
whatever it is from the
so
mean.
for B, now we have to take the value of the A, which is 1.33.
No, no, no. A is done.
Okay.
We're taking the Z value that we were given, plugging in the mean and the standard deviation, and getting out the X value that corresponds to it. So you see in the first question how we had 21 as our X value.
Hmm.
In the second question, I'm asking what X value is corresponding to this particular Z value.
So we gotta put 2.5, right?
Yeah. Hmm.
And then three, he makes it home in 3 minutes. Plus it
The
takes
three
them,
is a standard deviation, and
okay,
then 17 is the mean.
17 is the equals 9.5 minutes.
Hmm.
Okay. Why would I need to use this?
Well, you would need to use this if you were, say, like with Jack and Tina. You want to compare their test grades, right? But who did better? Like so the only way you can do that is if you have like this unitless kind of measurement to say, okay, yeah, Tina did better than Jack, you know?
Okay.
Yeah. So the basic structure of the formula for the standard score of a distribution is very general, right? When we verbalize the formula, we see it as the measurement minus the mean of the distribution divided by the standard deviation of the distribution. So we will use this general formula again and again. In particular, we will look at sample distributions, right, for the mean. And when we use the normal approximation of a binomial distribution, we'll see this formula. We'll also see it when we discuss the sampling distribution for proportions, right? Further uses occur in computations for confidence intervals and hypothesis testing, right? So low key, that's kind of summing up the rest of the semester for us right there, right?
But this, what you just put here, the basic structure of the formula.
Yeah, that's just kind of like giving you a little preview of what we're gonna get into by the end of the semester. 1 second.
As long as we don't gotta use probability, I'm good.
Oh yeah, that's what we're getting up to.
Are you serious?
Yeah.
Oh my God, I gotta go to tutoring for this because
Nah, this is way easier than what we did before.
Jeez.
Way easier. All you got to do is just copy the answer from the table, and that's it. All right, but let's tie this all in together right now. All right.
I like doing this at home.
Agreed.
Yeah, because whatever you say that's important, I could literally like copy and paste it
That's good. I
into
like
my
that.
phone.
All right, so standard normal distribution, right? So if the original distribution of x values is normal, then the corresponding z values have a normal distribution as well. The z distribution has a mean of 0 and a standard deviation of 1. So the normal curve with these properties has a special name. The standard normal distribution is a normal distribution with the mean equal to 0 and the standard deviation is equal to 1. Right? So I'm going to show you that picture. So any normal distribution of x values can be converted to a standard normal distribution by converting the x values to their corresponding z values. The resulting standard distribution will always have a mean at 0 and a standard deviation of 1. All right. So let me show you what we're getting into with that. All right, I'm going to show you what we're getting into with that. Do, do, do. So a little blast from the past, just a little. Do, do, do. Come on. All right, little blast from the past. So remember our empirical rule? Kind of putting it all together now, right? So for a standard normal distribution, our mean, mu, is equal to 0, and it's always going to be in the center, right? And then if we go to the right or to the left, one standard deviation, 68% of our data is captured in the middle, right? Two standard deviations to the right and to the left, 95% of our data. Three standard deviations to the right and the left, 99.7% of our data, right?
Yep.
Kind of tying this all in, right? So what we're trying to say is I could give you a story where I give you some X value, I give you some kind of mean, I give you some kind of standard deviation associated with it, right? And through the formula that we have, the Z formula, right? Z, I don't know why this keep freezing on me like this. One second. The Z is equal to X minus mu over sigma, that formula.
Yeah.
Through that formula, I can actually change a X distribution for some random X into a Z distribution. I could bring it back to this original formula right here, and I could get my answer easily, right? I could change an X into a Z, you know? So this kind of thing is very helpful. Very, very helpful. All right.
How can you change the X to a Z?
So you change the X to a Z by plugging it into the formula, and that's it.
Plugging it into that formula, X minus U, mu.
Mhm. Yep.
Yeah, because V equals whatever that is, right?
Mm-hmm. All that is.
So Z equals basically X.
No. X can be changed into Z and vice versa.
Let me write write that. X can be changed into Z,
Yeah, and vice versa.
and Z can be changed into X. X.
Hmm. Yep. And we have the two formulas to do it. You don't have to memorize it. They're all on your formula sheet. They're in chapter 7. Okay.
And Z can be changed. Z. So changing Z to X, how would you do that? I mean,
Changing
yeah.
changing Z into X, you use the raw score.
But you don't never need to use that, right?
Some questions maybe.
Mm,
So this is Z into X, and then
okay. Oh my, I wish I could have known that. Okay,
this
X.
is X into Z, right?
Okay, let me take a picture of that real quick.
Okay.
Okay. Is he that professor? I was
Mhm.
fine with my research. All right.
I got you. Sorry,
Mm,
so what does the standard normal distribution tell us? When we have the standard normal distribution, we know that the mean is 0, the standard deviation is 1, and any normal distribution can be converted to a standard normal distribution by converting all the measurements to the standard z-scores. All right. So areas under the standard normal curve, we have seen how to convert any normal distribution to the standard normal distribution. We can change any x value to a z value and back again. But, excuse me, what is the advantage of all this work? So the advantage is that there are extensive tables that show the area under the standard normal curve for almost any interval along the z-axis, right? Sorry for that. So the areas are important because each area is equal to the probability that the measurement of an item selected at random falls in this interval. Thus, the standard normal distribution can be a tremendously helpful tool, right? So you're going to see this probability is a lot easier than what we did before. Mhm. 1 second. All right, so using a standard normal distribution table. So using a table to find areas and probabilities associated with the standard normal distribution is a fairly straightforward activity. However, it is important to first observe that the range of z values for which the areas are given. The range is usually depicted in a picture that accompanies the table. So in this text, we will use the left tail style table, right? This style table gives cumulative areas to the left of a specified z, right? Determining other areas under the curve utilizes the fact that the area under the entire curve is 1. All right. So taking advantage of the symmetry of the normal distribution is also useful. The procedures you'll learn for using the left tail style normal distribution table applies directly to the cumulative normal distribution areas found on calculators and computer software packages such as Excel, Minitab, and SPSS. All right. So long story short, it's the same way that the calculator works in a nutshell, right? So knowing this way will help you to understand how the calculator is doing it for you.
What does that, I got lost. I don't know what that meant. Can you translate that?
I got you. So what I'm trying to say is that the way that our table works, right, in the packet is the same way that the calculator works, if that makes sense.
Our table, like in class?
So the formula sheet table, right?
It just
So let me show you more specifically what I'm talking about. 1 second. Hold on a second. Just bear with me 1 second. All right. So back to our formula sheet. Let me just pull this up, right? This our formula sheet, right? Let me just pull that out just a little bit. There we go. Right down here, chapter 7, there goes our raw score formula. X is equal to Z sigma plus mu. Our standard score formula, Z is equal to X minus mu over sigma. And the table that you keep hearing me mention, let me just go down real quick. This is my area for a standard normal distribution, right? So let's look at this picture right here in particular, right? So it says the table entries for Z is the area to the left of Z. This is what we were just saying a while ago, right? So all of these numbers in the table, right? These probabilities are areas to the left. They're less than Z, right? But
Oh,
whenever we get a question that's greater than or in between, we can manipulate this idea of being less than to get our final answer, right? And remember, I told you that the table will be split in two. We'll have one table that's less than Z, one table that's more than Z. So this is the less than Z table, right? That's why all of these are negative. But if you scroll down a little bit further, right, you have the table with the that's positive Z, right? These Z's are bigger than the mean, right? Well, we're gonna go over how to use this table right now, right?
Okay, so
See, 1 second. Okay.
hmm. So when Z equals negative 2.2,
Mhm. You can just look that up and you can find the probability of that. If it's less than, if you want less than or greater than, you can find a probability for both.
yeah, because this is the left side. We're talking about the left side right here.
Hmm.
And then the other side is no, this is the whole.
So let's look at this example, right? So standard normal distribution table. So we're going to use a table, right, to find the area under the standard normal curve, right? So let's look at this question. Find the area on the standard normal curve to the left of z equals negative 1.0, right? So graphically speaking, if I have a normal distribution like so, right here, this would be negative 1. Negative 1 is less than 0, right? And I want to find this blue area right here. I want to find the area under the curve for that, which is also the probability of z less than negative 1.0. That'd be written like this: probability of z less than negative 1.0, right? So here's how you do it. First, you want to shade the area to be found on the standard normal distribution curve as shown in the picture. Then notice that the z value we are using is negative. This means that we will look at the portion of the table 3 in the appendix for which the z values are negative, right? So this is our negative z value tables right here,
Okay.
right? Um, in the upper left corner of the table, we will see the letter Z, right? So these are Z's going down. The column under Z gives us the unit values and the tenths value of the Z, right? So for example, this is negative 3.4, right? Negative 1.1, negative 1.0, right? So it gives us the tenth value, doesn't give us the hundredth value, right? The next number after the decimal. So the column headings indicate the hundredth value of Z. So here's the hundredth value up top up here, right? 0.001, 0.01, 0.02, all the way up to 0.09, right? That's the hundredth value, okay? Table entries give area under the standard normal curve to the left of the listed Z value. So to find the area to the left of equals negative 1.00, we use the row headed by negative 1.0. Here it is, right? And then move to the column, right? Headed by the hundredth place, which is 0.000, right? And then this entry corresponds to what?
0.1587.
0.1587, right? So essentially, that's the probability that Z is less than 1.00. It's 0.1587.
Oh, okay.
And that's it. That's the whole probability thing that we're doing right now. It's copy and paste.
But but in the questions, it's gonna ask us like that.
Hmm. It's just flat out straight. Why is this thing loading right now? Come on. Okay. 0.1587. Sorry, I just wanted to write that. Okay.
Okay. Wait, can I write that on the formula sheet?
Sure. I mean, I don't know if it'll help you, but go ahead.
Okay.
And then this thing wants to move with me. Oh man. All right. Got my next thing here. Let's look at this one, right? In this question, I want to find the area to the left of z equals 1.18. So in this case, we're looking for the area to the left of the positive z value. So we have to look in the portion of table 3 that shows the positive z values. Again, we first sketch the area to be found on a standard normal curve like so, right? And and then we look in the row headed by 1.1 and move to the column headed by zero point zero 0.08, the desired area shaded, and we see that the area to the left of 1.118 is 0.8810. So let's take a look at that real quick. Let me get that table up for you. So here we go, right? If this was our positive table, we look at our z value right here. Here's where our z's are. I want to go down to 1.1. And then remember, the z value that we're looking for is z probability of z less than 1.18, right? So the 100th value is over here at the zero point 0.8. So we look at where do they intersect at, right? They intersect right there. So this is the 0.8810. And that's how you find it. Questions on this, anybody?
So the other one is negative and this one's positive.
Right.
Okay. And okay, is this part of the homework?
Mm-hmm.
Can we use this chart to do the homework?
Exactly. That's what I want you to do.
Okay, so how will we know like how we gotta do it when it says standard or something when you see Z, right?
They're gonna give you a Z, and if it's negative, you use the other table. If it's positive, you use the other table.
Okay, okay,
Mhm.
okay. Serenity, you gotta
Can we
pick
do
up.
another one? Can we do another one, Professor?
Yeah. I got like three more. I'm gonna do real quick, and then we got to kind of go a little bit left field. What happens when we're not talking about area to the left? We're gonna do a couple more examples like that too.
But is this is towards the right now, right?
Now this is still to the left. This is less than.
Why if it crossed that line?
So it's positive, right? But I still want the blue area to the left, right? Now, if the blue area was on the other side where the yellow is, that's another conversation. We're gonna have that conversation too, though. Yeah. All right, so here's a couple more examples, right? So table 3, areas of a standard normal distribution is located in the appendix as well as in the end papers of the text, right? So spend a little time studying the table and answer these questions. So as the values increase, do the areas to the left of z increase? All right. So yeah, right. As the z value increases, we move to the right of the normal curve and the area increases. So just to kind of give you a picture of what they're talking about here, let's say I had a normal distribution like this. Come on, man, really?
That's area C.
No, not C. Hold on. Trying to draw something real quick and it's like freezing on me a little bit. Come on. You can do it. Let me give it a minute. It's trying to work itself out. All right.
Hi, my baby.
All right. No thing. Let's try that again. Okay. Hallelujah. So what I'm trying to say, right? Let's say that we have okay. Say you have a normal distribution like this, right? Let's say you have a z value that's here. This would be a negative z, right? This would be the area to the left of it, right? And say we move z further along the right to the right hand side, right? Right? This is the area that I'm looking at now. So what they're trying to say is as z moves to the right, the area gets bigger, right? The area increases. That's what they're trying to say in part A, right? Part B, if a z value is negative, right, is the area to the left of z less than 0.5? All right, so yes, it would be, right? Remember that a negative z value is on the left side of the standard normal distribution. The entire left half of the normal distribution has area 0.5. So many areas to the left of z will be less than 0.5. So here's what they're talking about here, right? You already know that the entire distribution is 1, right? Come on, man.
So it's basically going from negative to positive, right? Because it keeps going up.
Well, area can't be negative. Remember, the area under the probability distribution is a probability. So remember, probabilities can only be between 0 and 1. It
Mm.
can't be negative. But here's what it's trying to say, right? If I have a distribution like this, right? Say I cut this in half,
Yeah.
right? Say you cut it in half, right? So this would be like 50% of your distribution, or 0.5, and this would be another 50% of your distribution, right? Or 0.5. This line that's cutting them in half, right?
So for grandma. What?
That line is where the 50% is, right? So any other z value that might occur out here is obviously going to be what you call it, smaller than 0.5. That's what they're trying to say for part two, right? And then let's look at C. If a z value is positive, or excuse me, if a z value is positive, is the area to the left of the z greater than 0.5? Yes, it is.
Yeah, it is, right?
Positive, right? For the same reason, right? Because we have a normal distribution. Oh, right? We have a normal distribution.
No, on hand.
We have a normal distribution, and when you cut it in half is 0.5. So what we're doing is we're pushing the z over the half, so it has to be bigger than 0.5. All right? Come on, man. What the? No, why this thing acting up all of a sudden? Everything was good. We were good. All right. Come on. It's just one of those days. Just one of those days. All right, you know what? Let's call it at that. I do see the time is 3:28. We finish at 3:30. Y'all probably want to get on with y'all days. You should have enough knowledge to knock out your homework. Your homework is literally just changing X values to Z values and changing Z values to X values. That's it. I was kind of trying to get a little bit ahead for the next homework, which is like asking you for the probabilities in which you have to look them up. All right. But we'll get more into that next week. All right.
What do you want? Probability.
Yeah. But I promise you it'll be simple though. It's just looking up what we were doing before.
Do we have to write our name on the chat?
Yeah, please. Yeah.
Okay.
Yeah. I've noticed that I'm able to see like when you come in, but just to be safe, just to be safe.
Yeah.
Yeah. So any questions about anything for today?
No, I think I understand it a little bit.
Awesome. All right, sounds good. All right, well, I want to wish you all have a good night. Have a great weekend this weekend, and I'll see you all on Tuesday, God willingly. All right. If you guys have any questions or anything, like please don't hesitate to email me, reach out. Remember that tutoring is available today, tomorrow, Saturday, Monday, if you guys have time to that you can spare to go. In person, CPH 303, online, via Zoom. I will be there on Saturday all day. If you guys want to meet up and do some homework problems together, that's cool as
Okay.
well.
Thank you so much, Professor. Have a good day.
Welcome. All right, you have a good night.
Bye,
Thanks.
Thank
guys.
you.
Bye. Bye.